Hi, everyone. Welcome to lesson 4 on limiting reagent and percent yield. What we're going to do today is begin to look at problems where instead of just being given the starting amount for one reactant and saying the other one is in excess, we're going to be given starting amounts for both reactants. And one of the things that we're going to have to do is figure out which reactant runs out first. Now, if you think about it, the reason why it's so important is because once one of those reactants runs out, the reaction stops, regardless of how much of the second reactant you have left over. So what we're going to do is we are going to look at some definitions to begin with for limiting reagent and excess reagent. So as you can see behind me and on your screen, the term limiting reagent refers to the reactant that runs out first. So we're going to look at an example where we're assembling some meals and one of our reactants, one of the parts of the meal, is going to run out first. That's what we would term our limiting reagent or limiting reactant. The one that we have too much of, or in some cases, multiple reactants that we have too much of or more than we need, those are called excess reagents. So at the top of this slide, it says, what does it mean for something to be a limiting reagent? So if you look behind me, we have all of the ingredients to make a double cheeseburger meal like we see on the right side of this slide. So for each of those meals, we'll need 1 soda, 1 fry, and 2 cheeseburgers. Now, when we're assembling this, we're going to have more than enough of some items and just enough of others. So your task is to figure out, well, which one of my items is going to run out first. So let's take a look at this together. So if we're assembling our meals, we're going to start off by using a soda, a fry, and 2 cheeseburgers. That'll make 1 meal. Now, if I do that same process again, 1 soda, 1 fry, 2 cheeseburgers, and I keep doing this until I run out of one of my components, you'll see that the first component that I'm going to run out of in just a second here will be my French fries. So at this point, I have put together 5 meals. That means I have 3 extra soda and I have 2 extra cheeseburgers. Those are your excess reagents. The thing that you ran out of first, in this case, the French fries, is your limiting reagent. Okay, so now bear with me. We're going to look at this same example, but we're going to make it look more like a chemical reaction. So take a look at this. So if you notice at the top, we start off with all of the components that we would need, and now we put coefficients in front of them so it looks more like a chemical reaction. And we set up our equations just like we set up our equations in the stoichiometry practice. So let's take a look. If our soda was the limiting reagent, this is what would happen. We have 8 sodas. 1 soda per 1 meal means we would be able to make 8 meals. If we just looked at our French fries, we have 5 French fries. There's 1 French fry for every 1 meal. So 5 times 1 over 1 would be 5 meals. And then if we looked at our cheeseburgers, we start off with 12 cheeseburgers. There are 2 cheeseburgers in every 1 meal. That's based on our coefficients from the balanced equation. So we would be able to make a total of 6 meals. Okay, once you determine the total amount of meals that you can make with each ingredient, what you want to do is look for the smallest amount. This is 5 in this case. 5 meals is the maximum amount of meals that you can make because after 5 meals, you won't have any more French fries left. So this is called your theoretical yield. Which is, again, the maximum amount that you could make. And this, the one that led to that theoretical yield, this is called your limiting reagent. By definition, anything that is not the limiting reagent is known as an excess reagent. So both cheeseburgers and sodas in this example would be considered excess reagents. Now, one of the things that we're going to do in accelerated honors is quantify how much excess we have. So I'm going to do that on the next slide. So in order to calculate the excess reagent, one of the ways that you can do that is start off with the maximum amount of meals or product, if we're talking about chemistry, that you could make, and then work backwards. So I made 5 meals. Each one meal required 1 soda. So that means I used 5 sodas. I started off with 8 sodas. I used 5. It means I have 3 left over, or 3 excess. In this case, in terms of cheeseburgers, I made 5 meals. Each one meal has 2 cheeseburgers. I used 10 cheeseburgers total. Started off with 12. I used 10. I have 2 left over as excess. Now, this was a silly example, but hopefully it illustrated for you what is meant by the term limiting reagent and what is meant by the term excess reagent. Now we're going to look at a much more practical example using a chemistry problem. Okay, if we look at the following problem, the first thing that you're going to notice is that for accelerated honors students, there is no equation given to you. Now, for honors and CCP students, you will be provided with an equation. You'll still need to balance it, but you'll be provided with an equation. In this case, let's start to write out what we have. We have 50 grams of ammonium chloride. And we are reacting that with 60 grams of barium hydroxide. For the purpose of this problem, we're going to consider both ammonium chloride and barium hydroxide as solids. Now, on the product side, hopefully everyone is able to recognize that this is going to be a double replacement reaction. On the product side, we're going to form barium chloride, which has the formula BaCl2. That's because barium is 2 positive, chloride is 1 minus. The other product that we're going to form, and this is where some of us missed it on the exam, the other product that we're going to form is the combination of ammonium and hydroxide. Now, this forms ammonium hydroxide. That's an unstable product that breaks down into ammonia and water. In this case, what we're going to get in terms of balancing our equation, we're going to put a 2 in front of our ammonium chloride to react with barium hydroxide. We'll need just one of these. So barium and 2 Cl's will be barium chloride, and ammonium, 2 of them, and 2 hydroxides are going to give us 2 ammonias and 2 waters. Water will be a liquid, ammonia will be a gas, that was on our reference tables, and barium chloride is going to be aqueous. Now, remember, chlorides are halides, and halides are aqueous except for silver, mercury, and lead. So barium is not one of those exceptions. Okay, now that we have our balanced equation, we can attack the problem. So this problem says, what is the limiting reagent? Now, that doesn't give us a whole lot of clarity because it doesn't tell us which product we should be forming. So one piece of advice that I want to offer to everyone is go ahead and look at part B. Sometimes when you're solving part A, you might benefit yourself by looking at part B and you can knock out A and B at the same time. So in part B, it says how many grams of ammonia are produced. So now when I'm going across and finding my limiting reagent, I can go to ammonia and I'll actually answer part A and part B at the same time. So let's take a look at this. So if I have 50 grams of ammonium chloride and 60 grams of barium hydroxide, and I'm converting it to grams of ammonia, I'm going to need some molar masses in here. Now, as I mentioned previously, at this point, most of you are very skilled in determining molar mass, so you no longer have to show the work for that. But remember that you should still be very careful when you're looking up molar masses off the periodic table, and I'll go through how the molar mass will be calculated up here. Now, we're going to start off by taking all of our ammonium chloride, so 50.0 grams of it, and we're going to convert it into grams of ammonia. So that's going to be a 3-step conversion. So my first step, just like we tried in stoichiometry practice, is to go from grams of a substance to moles. So that means we need the molar mass for ammonium chloride. So to do that, I'm going to bring up my calculator here. So ammonium is made up of nitrogen, that's 14.01, 4 hydrogens, so they're each 1.01, so that's 4.04 total, plus 1 chlorine. So chlorine is 35.45 grams per mole. So that gives us a molar mass of 53.5 grams. So we can put that part down here. 53.5 grams of ammonium chloride. Notice we put grams on the bottom, so it cancels out with the grams that we have on top. This is the number of moles of ammonium chloride. And remember, going between grams and moles, it's always 1 mole. In our next step, what we're going to do is we are going to use the coefficients from our balanced equation in order to convert from moles of ammonium chloride to moles of ammonia. Now, to highlight this, I'm going to use a specific color, a different color, in order to highlight where I'm getting these numbers from. Poof, and just like that, notice that all of my coefficients have now turned green. So in our next fraction, we're going to be switching from ammonium chloride. So down here at the bottom, I'm going to put 2 moles of ammonium chloride, and we're going to moles of ammonia. So I'm going to put 2 moles of ammonia on top. Notice, even though we have 2 moles of ammonium chloride in our balanced equation, when we're going between grams and moles, we still figure out the mass for 1 mole. The only time that we use the numbers from the balanced equation is when we're converting from one substance, in this case ammonium chloride, to a different substance, in this case ammonia. Okay, on our last fraction, we need to include our molar mass for ammonia. So again, even though there's a 2 up here, because we're going from moles of ammonia to grams of ammonia, we're not changing substances. We're going to find out that our molar mass is 17.04, so 14.01 for nitrogen, plus 3.03 for our 3 hydrogens. So we wind up with a molar mass of 17.04 grams. And now we can look at our entire equation here, cross out our units. So grams of NH4Cl, moles of NH4Cl, moles of NH3, and we're left with grams of NH3. Again, no different than what we did in the stoichiometry assignment. Now, typing this into the calculator, we have 50 divided by 53.5 times 2 divided by 2. We don't even have to put that into the calculator because they'll cancel each other out, times 17.04. We wind up with a mass of ammonia that is equal to 159 grams. So now we need to do that exact same process, but this time we're going to start off with our barium hydroxide. So we're going to make another line below that one, 60.0 grams of barium hydroxide. We're going to take that to ammonia. In order to determine the limiting reactant, you have to take both of your reactants to the same product. So you must take both reactants to the same product in order to determine which one runs out first, which one of your reactants runs out first. So if we take a look here, we have 60 grams of barium hydroxide. So the first thing that I need to do is find the molar mass of barium hydroxide. So if you look on the periodic table, barium is 137.33 grams. I have two oxygens, each one is 16, so that's 32. And I have two hydrogens, each one is 1.01, so that's 2.02. Sorry about that. So we get a molar mass of 171.35 grams. In our next fraction, we're going to convert from moles of barium hydroxide, which is the unit that we have now. So if we cross out units, notice that grams are now gone. So moles of barium hydroxide, and we're going to convert it again to moles of ammonia. So using our special color that indicates that we're pulling a coefficient, we have 1 for barium hydroxide, so 1 mole of barium hydroxide, and 2 moles from right here, 2 moles of ammonia. Then the last fraction is going to be exactly the same, and that is going to be 1 mole of ammonia on the bottom and 17.04 grams of ammonia on top. Looking at our units, we're going to cross out barium hydroxide in grams. We're going to cross out barium hydroxide in moles. We're going to cross out ammonia in moles, and we're left with a unit of grams. So now we're going to pull up our trusty calculator. We have 60 divided by 171.35. This time we are going to multiply by 2 because it's on top. And then we're going to multiply by 17.04, again, because it's on top. And we get an answer of just 11.9 grams. Okay. This part of the problem is similar to this part here of our previous kind of silly example with our McDonald's food. We took all of our reactant and said, how much product could I make? Then we took a second reactant and said, how much product could I make? And then we find, okay, which one of those is the smallest one? So in this case, it was the 5 meals. In our case, it is the 11.9 grams of ammonia. Now I want you to think about this for a second. The bigger answer, I want you to cross that out, highlight it in red, somehow indicate that that never happens. So I like to do this, just so I never accidentally use that part in any other portion of the problem. So I'll never get 150 grams of ammonia, because once I reach 11.9 grams of ammonia, I've run out of my barium hydroxide. Okay. So when we looked at the McDonald's example, I told you that this would be called our theoretical yield. The one that gave you the smaller amount, so in this case, that's barium hydroxide, this is called our limiting reagent. The one that gave you the bigger amount that never happened, that one here is called our excess reagent. Now, let's go back and take a look at the problem. In part A, it asked us to determine our limiting reactant or limiting reagent. We did that. We identified that as barium hydroxide. So I'm going to put an A there just to tell us that that's the answer to part A. In part B, it wanted to know how many grams of ammonia we could form. Now remember, we were smart. At the beginning of this problem, we looked ahead at B, and when we figured out our limiting reagent, we said, they're going to ask about ammonia in part B. I should go to ammonia in part A, and that way I can solve two problems at the same time. So in part B, our theoretical yield of ammonia, we have now also solved for. Now let's take a look at part C. In part C, it said, a student completes the reaction and only produces 10.3 grams of ammonia. Remember, we were supposed to get 11.9. It says, what is this student's percent yield? This is a new calculation that we're learning for the first time today. So I'm going to give you the formula for percent yield, and then we're going to calculate it for this problem. So percent yield is equal to the experimental amount, the amount that you got by doing the experiment, divided by your theoretical amount. Times 100. So in this example problem, the student was able to recover 10.3 grams of ammonia. The theoretical amount, the maximum amount, if everything went completely perfectly for them, the maximum amount that they would have been able to get was 11.9 grams. So in this case, we would wind up with a percent yield of 86.5%. It's not bad. So if everything went perfect, they should have gotten 11.9 grams, but some of it was lost. Especially when working with gases, it's easy for some of your product to get lost. All right. So at this point, those of you in CCP and honors can turn off the video. The very last thing that I'm going to do is for accelerated honors only, and that's just calculating the amount of excess reagent. So for those of you in CCP and honors, have a great week. For those of you in accelerated, we're almost done. So the last question up here says, how many grams of excess reagent, so we know our excess reagent is ammonium chloride, remain after the reaction is complete? So if you think back to that McDonald's example, we can start off with the amount of ammonia that we made. You can actually also start off with your limiting reagent. It's up to you. So we're going to start off in this case with our 11.9 grams of ammonia. We're going to do the same thing and we're going to work backwards. So we're going to go from grams of ammonia to moles of ammonia to moles of ammonium chloride, our excess reagent, and then finally to grams of ammonium chloride. And we have most of the numbers that we need already. So let's take a look. 1 mole NH3 is 17.04 grams of NH3. Next one, based on our balanced equation, we have 2 moles of NH3 for every 2 moles of ammonium chloride. And then finally, our molar mass for ammonium chloride we found earlier. So 1 mole of of ammonium chloride is equal to 53.5 grams of ammonium chloride. So getting this across, we have 11.9 divided by 17.04 times 2 divided by 2 times 53.5. And that is equal to 37. I'm going to round it to 3 significant figures. So 37.4 grams of ammonium chloride. Now, be careful. A lot of students get to this point and say, bam, got it, 37.4 grams excess. Not so fast, right? This amount, 37.4 grams, doesn't represent the excess. Instead, it represents the amount of ammonium chloride that was used in making this 11.9 grams. So if you want to put a label on this, you can label that as used. Now, what we're going to do next is we're going to figure out our excess. So if you remember, in the beginning of the problem, we started off with 50.0 grams of ammonium chloride. That's what we had at the beginning. We used 37.4 grams of ammonium chloride. That means we'll wind up with 12.6 grams of ammonium chloride as our excess. Alrighty, I know that was a lot. If you have any questions, please stop by office hours or set up an appointment with me or email me or send me a message through Schoology, anything that you want to do, and I'll be sure to respond as soon as possible. All right, I hope everyone has a great week. Again, try the problems, check your answers. Let me know if you have any questions. Thanks, everyone.